Okay, so what's the big deal about quantum? Why is everybody talking about quantum these days? The fact of the matter is that quantum science is really quite old, more than 100 years old. What is new is the weird parts of quantum mechanics. Now, the fact of the matter is that we've known about these really weird features of quantum mechanics, the things that Einstein thought were so weird that it couldn't possibly be true, but it is. We've known about them for almost 100 years. What we haven't done is make those weird features of quantum mechanics part of our technology. Most of the technology that is dependent upon quantum mechanics, our cell phones, our video lives, almost everything that has to do with consumer electronics has to do with quantum mechanics. The things that are new are using the weirdness of quantum mechanics. Those things that I mentioned, cell phones and videos and computers and all of that, don't rely on the weird aspects of quantum mechanics. They rely on some of the most important features of quantum mechanics, but they don't rely on the really weird aspects. What's coming now, what is causing so much interest in both the scientific world, the technological world, and with the general public, is putting the weirdness of quantum mechanics to work. This is the sort of thing that makes possible quantum computing, a feature, a use of the weirdness of quantum mechanics that, if it comes to full fruition, will be able to do computing feats that we can't even dream of with our computers of today. This is what's really exciting about the present day. Well, I've been so pleased with the award of the Nobel Prize in physics this year to Alain Aspect and John Clauser and Anton Zeilinger. These are all people I know well, but more importantly, the work that they have done really represents to me the beginning of the modern quantum era. And what it signifies is a recognition of the importance of the features of quantum mechanics that are the hallmarks of what I've called the second quantum revolution. It's not so much that this represents a change in the attitude toward investment. I think that what it represents is the success of these new features of quantum mechanics to do interesting things. And those successes have been recognized by this year's Nobel Prizes. They were recognized by the Nobel Prizes of 2012 to Dave Wineland and Serge Haroche, who did experiments with single quantum objects. That too is a hallmark of the current second quantum revolution. And so what we see here in the award of these Nobel Prizes is a recognition of the successes. And it is those successes that have brought investment, that have brought investment by funding agencies for doing basic research, that have brought investment by venture capitalists to fund startup companies, to do the engineering work of bringing this new kind of quantum mechanics, or at least newly interesting kind of quantum mechanics to the marketplace. It's those successes. And that's what we should be concentrating on, is getting more of that kind of success that's going to lead to the kind of investment that will lead to more success and a more effective bringing of these kinds of basic research results into the marketplace. So the question of what it's going to take to get quantum science adopted as part of technology really depends on the specific kinds of application that one envisions. Let's take one example, a really huge endeavor where the adoption of quantum technology has made a huge difference. LIGO, the Laser Interferometer Gravity Wave Observatory. This device, which in the past few years has seen the first direct detection of gravity waves, which has led to a Nobel Prize for the people who have led this effort. This enterprise is one of the most sensitive measurements that's ever been made. And it is made even more sensitive by using what is known as squeezed light, light that is intrinsically quantum, so that it gives what we call a quantum advantage over using more ordinary light, the light that comes from a laser, for example. This squeezed light allows these devices, these laser interferometer gravity wave detectors, it allows them to detect things more sensitively. It really reduces the noise so that you can see smaller signals rising up above the noise. And this has been huge. It has allowed the reach of these gravity wave detectors to go further out into space, to see more and more events. And it seems that each time a new event comes along, we learn something new about the way the universe works. So this I find to be incredibly exciting, and it represents one of the most magnificent applications of the second quantum revolution, where we really get a quantum advantage, where we do something different that we couldn't have done. Why was that possible? Well, one reason was that people learned how to make squeezed light in the way that it could be used in this kind of a device, but it also meant that those devices had gotten to the point where they couldn't get any better except by using squeezed light. In the past, these interferometers were made better by increasing the laser power, making the mirrors bigger. That line of improvement had played itself out. There wasn't any place to go except the quantum way. And it just makes me feel so good that quantum advantage has played out in such a wonderful and fruitful way. But that's only one example of how the second quantum revolution can affect things in an important way. Let's say that what you want to do is to make a quantum simulator, something that will teach you something about the way in which quantum many-body systems work. Now, the trouble with quantum many-body systems is that the difficulty of calculating the behavior of a quantum many-body system grows exponentially with the number of bodies that are in the system. That means that, for example, if I add one more body, one more, say, spin to try to understand what a quantum magnet does, I add one more spin to it, it doubles how difficult the problem is. A quantum simulator using the rules of quantum mechanics intrinsically in its operation can get around this. That is, it already has built into it the ability to do this kind of exponential scaling with the number of particles. So if you add another particle, then it'll handle it because it's a quantum mechanical device itself. Now, what is the challenge there? Because we have such simulators, they're just not very big. The challenge is adding more qubits and keeping them coherent. The ability to have these quantum bits, these qubits, which are the intrinsic building blocks of any kind of a quantum processor, to keep their quantum coherence, to not be messed up by their connection to the environment. This is one of the key challenges, and it is the thing that we're going to have to work on in order to make really useful simulations. A lot of people are working on it. A lot of people are making great progress. I just heard today of another factor of 2 improvement in a certain kind of qubit, and I'm really looking forward to seeing the paper when it comes out. So those are just 2 examples of the kinds of things that we need to have happen in order to make further progress to bring these things to full fruition. Well, as a quantum physicist, the thing that I am most eager to see as an application of uh, the second quantum revolution, of the weirdness of quantum mechanics, of entanglement and superposition, the thing that I am most eager to see is to unravel the behavior of many-body quantum systems. Because of the exponential scaling, which I've talked about before, we cannot use ordinary classical computers to do computations of many-body systems that exceed a few tens of elements, assuming that those elements become entangled with one another. Now, I haven't talked about what entanglement means, but it's a connection between objects which could be distant or could be quite close, where the fates of the uncertain outcomes of those systems are entangled. That is, if a certain uncertain outcome is observed in one of them, then it affects what the previously completely uncertain outcome in another one would be. That's what entanglement is about. And it dominates the behavior of quantum many-body systems, but it's almost impossible to calculate classically when there are very many elements in your many-body system. But quantum simulation promises to provide the means of doing these kinds of calculations without using a classical computer, but instead using another quantum system to, in a sense, emulate the behavior of the quantum system you're interested in. There are a lot of quantum many-body systems whose behavior we do not understand. One of the most famous is high-temperature superconductivity. Nobody really has a very clear picture of exactly how high-temperature superconductivity works, but it's something that we desperately want to understand better. And one of the dreams that we have is that quantum simulators, or possibly quantum computers, may be able to give us the answers that we're looking for. So for me, this is the thing that I'm most excited about, is learning more about the way quantum systems work. Let me begin by saying a little bit about what I see as the importance of diversity. If we're going to make the most effective progress in this quantum enterprise, we need to have the best people, and we need to have people with different perspectives who come together to find the solutions to hard and important problems. Now, the realization of quantum technology is not only an engineering problem. There are unsolved scientific problems, and there are plenty of challenging engineering problems. And hard problems, in my experience, are often best attacked by people who have varied perspectives. And that's where diversity comes in as an important component. We cannot afford to write off any groups that are now, for example, underrepresented in physics and in quantum fields. We can't afford to write any of these off because we need the perspectives of as many different kinds of people as we can get to work on these hard problems. Now, how to do it? I don't really know if anyone knows the answer to that. I don't know that anyone knows what is the magic bullet. But there are lots of ideas. At the University of Maryland, where I work, we are developing a program within our Quantum Leap Challenge Institute for robust quantum simulation, where we are mentoring students from underrepresented groups. We're partnering with a local historically Black college or university, and we are mentoring these students, meeting with them on a weekly basis for a couple of hours and talking about physics, and particularly about quantum physics. I see this as a kind of a retail way of doing things. This is not going to change the demographics of how many underrepresented minorities are working in quantum science, but it's going to change, I hope, the lives of these few students. And if we can publicize this kind of activity and get more people in more places, in more universities, in more research programs doing this kind of thing, if it turns out to be successful, then maybe we can change the demographics of the people who are working in this great quantum enterprise. But we have other approaches. People are taking also what I would call a wholesale approach, developing quantum curricula that are going to be able to be used widely throughout the country, throughout the world, to reach in a more effective way underrepresented groups. So I think that both the retail approach that I am engaged in right now and the wholesale approach that other people are engaged in are both things that have a great deal of value. What's going to work really remains to be seen. We've been working for decades on trying to improve the participation of women in science. And we still don't really know what the magic bullet is. And we've made a little bit of progress over the decades that I've been working on this. And there's a lot more progress to be made. But the only way to figure out what to do is to try it and see what the results are. And that's what we're doing now.